Okay, this is 12-6. In this problem we want to determine the equations of the elastic curve for the beam using x1 and x3 as noted here. Specify the beam's maximum deflection. Alright, to do these problems, the first thing you want to do is draw yourself some rough free body diagram of what the reaction forces are going to be at A and B. Obviously this one we can tell we have no other horizontal forces, so this has got to be 0. So what I'm going to do first to find this force FB, I'll take a moment at A. So I'll take a moment at A and set that equal to 0. When I do that, I will get the value of P times L plus L over 2. We'll make that negative going this way, plus the force at BY times L is equal to 0. Here we'll get minus P, oops, make that better here. We'll get a minus P times L, and that would give us 3 halves, 1/2 plus 1. So I'll just change that to minus 3 over 2 plus FB y times L is equal to 0. Solve FBY, or FB, it doesn't matter, is equal to 3 over 2 times P over L divided by L's. L's will cancel out, so we can say the summation of forces FBY, or FB, whatever you want to say. I'll just say FB because that's our only, has no horizontal force, and that's all I mean, is 3 over 2 times P. Next thing we do, we sum the forces in the y direction. We set that equal to 0. When we do, we get FAY plus 3 halves times P minus P is equal to 0. We'll solve, move everything to the other side. We'll subtract these. We get FAY plus 1/2 times P is equal to 0. FAY is equal to negative 1/2 times P. So we know right now we have this going the other wrong way. So we need to just reverse that and go back the other way, because the reason being we got a negative here. Again, it makes no difference which way you orient this to in the beginning, because when you sum your moments and sum your forces, you'll be able to tell that right off. Alright, so far so good. Okay, now what we want to do here is we want to go back to the definition that, I'll write this down, is that E, moment inertia, times I is equal to the second derivative of the deflection with respect to dx squared, and we set that equal just to our moment of x. Alright, so here you're going to have to really set up two of them. We're going to start right here, and we're going to draw a small section of the beam itself. I'll just get a shape. I have a force coming down. This is P over 2. We're going to let this distance here be x. We can tell now all we're going to do is we're going to take a moment right here. There's two things we know. We know our force coming down here is going to be P over 2. Oops, make that a little straighter, sorry. That has got to be P, make it black too. This has to be P over 2 coming down here, that's your shear, and then this is causing a moment to go back this way here. Okay. So now we can rewrite this as EI go back and write that EI times the d squared v over dx squared is going to equal to minus p over 2 times some x1 value. We're letting this be x1, and that's going to cause the moment. Alright, so now all we're going to do is we're going to rewrite this as d squared v is equal to minus p over 2 x1 dx squared. Or the second derivative anyway. Now at this point we're going to integrate. So we're going to integrate this side, and we're going to integrate this side, and when we integrate this side over here, we will just go back, and that gives us EI dV is equal to minus P x1 squared, and divide by the 2, and that gives me the 4 down here, plus C1. And then we have our dx squared here. And again, you can move this back down to the other side if you choose to. It really makes no difference. But all this is times, I'm sorry, not dx squared, dx, because we've integrated. Alright, now you can leave it like that, or you can bring it right back down here and put a dx here. It makes no difference. Alright, so really what we're going to do, we're going to integrate this thing one more time. And if you want, bring the dx up before you integrate, which I guess I'm going to go ahead and do. Now we'll integrate this side, integrate this side here. And when we do this side, now we're going to get the E, the I, this goes to V. Now this is going to go third power and then divide by 3. That gives us minus P x1 to the third over 12. That gives us plus C1x plus C2. Alright. So far so good. So we're getting these two equations here. Alright, now if you want to at this point, you can go ahead and determine some of your condition points. We know that when x1 is equal to 0, here, when this value is x equal to x1, we go back to our picture here. We let x1 be 0, we're going to get no deflection in this point here. It's supported, so there's no deflection taking place. So we can say x1 is equal to 0. Then we know that v is equal to 0. Okay, so we will get E times I, and we'll call this our V1 because it's our initial one, is equal to minus P times x1 cubed divided by 12 plus C1 x1 plus C2. Now at this point here, we can set up our boundary conditions, and that's what you want to do because you want to determine what the C1 and C2 are. And you can either do it now or do it later. It makes no difference. So I got my boundaries. I don't know why I said boundary conditions. Okay, we'll go back up to our upper picture and we'll look at our boundary conditions. There's things we know here. We know that when x1 is equal to 0, when this value here is equal to 0, then we know that v1 will equal to 0. We know when x1 over here is equal to L, then we know v1 is also equal to 0. We have no deflection. So now you apply those boundary conditions down here. x1 equals 0, v1 equals 0. x1 equal to L, v1 is equal to 0. I'm going to apply the conditions here. I'm going to let my deflection go to 0. Here I have E times I times 0 equal to minus P put my 0 in, cubed over 12 plus C1 times 0 plus C2. Now look what happens here. You have zeros, you have zeros, you have zeros. So C2 must equal to 0. Now you apply your other boundary condition. This one right here. You let, and again, you let your deflection be 0. And when you do, you get E times I times 0 is equal to minus P times L1 cubed over 12. And again, I don't know why I'm putting L1, just L. Let's change that. I'll change it up here too. L cubed plus my C1 I had here times L is, and all that's going to equal to 0 because we have a 0 over here. Move this to the other side. I'm going to get C1L is equal to PL cubed over 12. I divide by the L here and here. That gives me a 2. So now you know that C1 is equal to PL squared over 12. So what's happened is you've taken this equation right here and now you rewrite it because you've defined it as EI V1 is equal to minus P times X1 cubed over 12 plus PL squared over 12 times X1. Okay, so now we're going to circle this one, and now we're going to go back to, I'll show you up here. Now we're going to look at what happens as we go on the other side of this, which is our X3 value. So now I'm going to draw a small section of that beam. So when I do that, I have a beam that looks kind of like this. Like here, we'll go ahead and apply the loads that we already have. So we have P over 2 coming down. Black. I have this value here, which is what's happening at B, and we already have B as 3 halves P. So now what we're going to do is basically we're going to take a moment around this distance right here. Slide this over here. Well, this distance here would represent X3. We know this distance is our L, so this distance here would represent X3 minus L. Okay, now we'll take a moment at this point here. I'll scroll down here. Let's call that, what do we want to call that? Let's call it point C or something like that. So if I take the moment around C, well, again, anything goes this way, we'll let it be negative here. I will get minus P over 2 times X3 plus 3 over 2 P times X3 minus L. And we're going to again figure out what that's going to be. That's going to give me minus P X3 over 2. We'll distribute this, and that'll give me plus 3 over 2 PX3 minus 3 over 2 P times L. Here we can simplify that as 1. Let's say 3 over 2. Oh, we got to subtract 1, so we'll clarify that. So when I do that, that's just going to give me P times x3 minus 3 over 2 times PL. And that's going to be my moment at x3, or the moment at C. Alright, now we go back to what we did before. We set up as EI times the second derivative of my deflection with respect to x. And we'll make this to be x3. And we know that's going to equal to what is going to be equal to our moment at x3. So we're going to set that equal to the right value here, which will be equal to px3 minus 3 over 2L. Now again, basically you're moving this up and you're going to integrate. So I'm going to just simplify a little bit as I go. So if I integrate the left side and move the x up in respect to v, then I would get dv is equal to, and then we're just doing this part here. So when I integrate the first part, I will get p over 2 x3 squared minus 3 times, I left my p out here, 3 times p, 3 halves pl times x3, and then we got to add our c plus, in this case we'll add c3. We integrate this again on this side here. I'll get EI times V is equal to P. We do the cubed and then make this, that'd be P over 6 x cubed to the third power minus, integrate that, 3 over 4 PL x cubed, I'm sorry, x3 squared plus C 3x3 plus C4. Now this one's a little different, and the only boundary conditions when you get into here would be when x3 is equal to L, then our V is going to equal to 0. That's the only boundary condition we have here. So we can, our boundary condition would be this, that V3 is equal to 0 when x3 is equal to L. That's the only boundary conditions that we have. So let's see if we can simplify something. Okay, so we go back up to here and we say that EI times 0 is equal to P over 6, we let x3 be L cubed, minus 3 over 4, we got P, we got L, we let this be L squared, and then we have plus C3L plus C4. That's all we can do here. At least these we can combine here. So when we do that, we can add these two together. Let's do this. Let's see. We go up to 12. That'd be the fastest thing we could do. We could do 2pl cubed over 12 minus 9 over 12, and that would be pl cubed plus c3l plus c4. We simplify that, that gives us minus 7 pl cubed over 12 plus c3l plus c4.